Well, hello, A&P class. We're on now to our second to last class for the semester. So today we'll do regulation of urine and body fluid, and then we'll have one more class on Friday. So hope you guys are all doing well and getting ready for that final that's coming up. So we're going to dive right into this. One thing that just to note, when you guys printed up the slides, you have a clicker question that starts here first called preview or review question. And that one I moved towards the end because we hadn't covered those hormones yet. And so it's not really a review question. It would just be purely a preview question. And so we need to talk about it a little bit first before you have any of those answers. So let's do that. So we're going to start with all of the different hormones here that regulate body fluid and urine output. And we're going to talk a little bit more specifically about where they work and how they work in the kidneys and other places in the body. So we'll start with ADH. We've already talked about ADH, and we know that it's released from the posterior pituitary gland. The two main stimuli for it being released are the osmolarity and extracellular fluid, okay? And that's going to be detected by osmoreceptors. They're a special type of chemoreceptor, and specifically in the hypothalamus. Okay, so now if our blood, if our extracellular fluid becomes hypertonic, meaning it's highly concentrated, that's going to increase our ADH. If it goes the other way, if we start getting diluted or not very concentrated, then we'll decrease ADH release. Also low blood pressure, which really means low blood volume, and that's detected by baroreceptors, and those are pressure receptors, right? And so these are not as sensitive as the osmoreceptors. We need about a 5 to 10% decrease before action, and that's kind of why it's important to start drinking before you even feel thirsty. And these are located in the heart, in the large veins, carotid sinuses, aortic arch, all these places that have large amounts of blood in them. Okay, so when we have low pressure, we increase ADH release. Okay, so those are the two main stimuli for release. Those are the action, or those are the where we find those receptors and how those are sensed. And then the actions are, number one, increase water permeability in the collecting duct, right? So where that collecting duct was already permeable to water, and this gives it more permeability to water. So as that fluid passes by that strong concentration gradient, that highly concentrated fluid in the interstitial space around the collecting duct was set up by the loop of Henle that we talked about last time. When that water passes, or that filtrate passes by that, since with ADH on board, it makes it more permeable to water, and so more water flows out. Okay, and that's going to make for more concentrated urine and less urine. Okay, it also increases water permeability in the distal tubule, so we get more water back in the distal tubule as well. Okay, so the overall effect of ADH is less water loss in the urine. Okay, the negative feedback of this is when we just reverse those two stimuli, right? So we decrease osmolarity of the extracellular fluid, or we increase our blood pressure, that's going to decrease ADH release. Okay, so ADH is also affected strongly by alcohol. Okay, and alcohol is a diuretic, right? It increases water loss. And how does it do that? It actually binds to the posterior pituitary gland and stops the release of ADH. So it inhibits the release of ADH, and that's how alcohol affects. That's why alcohol is a diuretic. Okay, it stops the antidiuretic hormone from being released. Okay, so the effects on the collecting duct and distal tubule don't reabsorb as much water because of this. Doesn't really affect electrolyte balance because salt will typically go with it, but it does does cause dehydration. Other diuretics that act in this pathway, Lasix is a very common diuretic, also known as furosemide. Furosemide is what's known as a loop diuretic. Okay, and what that does, it's a little bit different than the ADH or than alcohol. Alcohol blocks ADH release. Loop diuretics are a little different, where they act in the ascending limb of the loop of Henle. Remember, that was the part where salt was pumped out or sodium was pumped out. So this furosemide blocks those little salt receptors that grab onto those sodiums and pump them out of the filtrate. Okay, so we block reabsorption of sodium in the ascending loop of Henle. And so then to think about that, how would it make us lose more water? Well, because this would make it so we don't create that strong gradient next to the collecting duct. I'm just going to do CD there. Okay, if we don't create that strong gradient next to that collecting duct, because we pretty much stop the counter current multiplier mechanism, right? If we stop the reabsorption of sodium on the one side of the loop of Henle, then we're pretty much disrupting that whole counter current multiplier mechanism. We don't concentrate the interstitial space as much deep in the medulla of the kidneys. We don't create that. We don't set up that strong gradient. Water is not going to get pulled out as much when it passes by that deeper part of the kidneys in the collecting duct. Okay, what about diabetes insipidus? So diabetes insipidus is a totally different thing. We talked about this a little bit already. Totally different than diabetes mellitus, right? Diabetes mellitus always has to do with sugar, blood sugar, right? We talked about that, how diabetes mellitus mellitus means like honey, sweet tasting, because their urine, the urine in diabetes mellitus patients is sweet. The urine in diabetes insipidus patients is tasteless. Okay, and that's what insipidus means. And this is either a lack of ADH or a lack of ADH receptors in the kidneys. What does this do? This makes for lots and lots of very dilute urine. Can be up to 3 to 20 liters per day. Major dehydration, this can be life-threatening if it's not taken care of. Okay, so the ADH recap here. A is the stimulus. We work our way down. B is the receptor. All right, so it's stimulus there, extracellular fluid, increase in osmolarity, increase in sodium concentration in the plasma, as well as the low blood pressure would do it as well. Okay, and that's showing that here, right? The low plasma volume, low blood pressure. Okay, so then that's going to go to those osmoreceptors in the hypothalamus. Okay, and then that is going to lead to C, which is those baroreceptors. Okay, so we get stimulation here, and we get stimulation here. So D is the posterior pituitary gland. We know that's where it's released from. E is the hormone, right? That's ADH. What does it target? It targets the kidneys, primarily the collecting duct, also the distal tubules. Okay, and then the effects are increased water reabsorption, and the results are decrease in urine, increase in plasma volume, decrease in extracellular fluid osmolarity. Okay, so what's the negative feedback? It's this right here, right? This is the negative feedback, stopping that stimulus. Okay, what about this one? Renin, angiotensin aldosterone axis, or the renin angiotensin aldosterone system. Okay, this is the whole process. We talked about this a little bit already, but I'm going to give you some more of the details here that you didn't have last time. Let's start with renin. So renin is released by those granular cells in that juxtaglomerular apparatus of the kidneys, right? We talked about those granular cells. What did they do? They sense blood pressure, right? They sense how much blood pressure is coming in on those little arterioles around the glomerulus. And if the blood pressure goes low, then they release renin, right? If blood pressure is low, they release renin. And what happens when they do release renin? See that in a second. So we decrease blood pressure sensed by those granular cells, or low concentration of sodium sensed by the macula densa. Okay, either one can do that. Okay, so in the chain of events here, renin is not really a hormone, it's more of an enzyme. And so renin, once it's released, it's going to interact with a protein that's always in the blood, because it's a plasma protein made by the liver called angiotensinogen. Okay, that angiotensinogen gets converted into angiotensin 1 when it interacts with renin. Okay, so renin turns angiotensinogen into angiotensin 1. Okay, and that angiotensin 1 is then converted into angiotensin 2. And that happens via an enzyme called the ACE enzyme, or the angiotensin converting enzyme. Okay, and that one is made in the lungs. All right, and then we got all kinds of actions of angiotensin 2 here. We have increase in thirst, salt craving, causes ADH release, causes aldosterone release. That's the one we talked about before. Activates our sympathetic nervous system, which then that causes vasoconstriction. And then it also directly constricts the efferent arteriole in those glomerulus, in the glomerulus, and then that gets our GFR back up even though blood pressure is low, right? So if we constrict the efferent arteriole, then we're making blood spend a longer time in the glomerulus, which would push out more filtrate. Okay, so there's a lot there. So let's look at this. So then the aldosterone piece of this is obviously connected to this because aldosterone, one of the stimuli for aldosterone release is the presence of angiotensin II. So where does aldosterone come from? It comes from the adrenal glands, specifically the adrenal cortex, stimulated by two things. The one we just mentioned, angiotensin II, and then secondly, high potassium. Okay, so its actions are we increase sodium reabsorption, so we bring back more sodium, and then secondly, we get rid of potassium, we secrete potassium. And then because we're bringing in that sodium, water follows that, it reabsorbs water as well. So in the end, we get water and salt conservation, and then it also has the effect of constricting the afferent arteriole. Okay, so we constrict the afferent arteriole of the glomerulus, and so that means, again, in this case, we're not sending as much blood into the glomerulus, so that's going to decrease filtration. Okay, these are all measures to help us hold on to more fluid, right? And really, when we think about aldosterone, we want to think about salt. Okay, this one's primarily looking at, primarily controlling our salt levels, our sodium levels. Okay, so the overall results: less urine, more dilute urine because we pulled back the salt. Okay. We all also know that caffeine is a diuretic as well, and so caffeine, being a diuretic, works in a little bit different way than we talked about with alcohol. This one works with aldosterone. This one blocks the effects of aldosterone acting on the kidneys. Remember, alcohol blocked the effects of, or blocked ADH release. Aldosterone blocks the effects of caffeine blocks the effects of aldosterone on the kidneys. Okay, so this is a nice image for you to take a look at. All right, so this nice flow chart here walks us through this very clearly, this whole system, and this is one you definitely need to know all the details of. And this, again, is that renin, angiotensin, aldosterone system. Okay, so the green ones are the stimuli, yellow are the hormones or an intermediary protein. Blue is an action, an intermediate action. Black would be the actions of angiotensin II, and then red is our final outcome. So I would encourage you to pause it, see if you can fill this in, and then come back and also see if you can answer this question up here. Okay, so let's start with the stimuli. Stimuli are decrease in blood pressure, right, which decreases GFR, okay, which is going to be sensed by those kidney cells that we were just talking about. Those juxtaglomerular cells release the renin, right? Renin's released, and then we see there that the liver is the one that's making the first protein, angiotensinogen. Remember, that's just always in our blood. If it interacts with renin, like it is here, then renin turns it into angiotensin II, and then angiotensin II interacts with another enzyme that's just, again, always in our blood, but it's made by the lungs. It doesn't have to go to the lungs to do this. It's just in our blood. And this enzyme is called the ACE enzyme, angiotensin converting enzyme. One interesting note about that enzyme that's very relevant to today is that it's been shown that the coronavirus enters into our cells by binding to an ACE enzyme. It's actually the ACE2 enzyme, which is found on outside of many of our cells. And so it binds to that, and that's its entry point into our cells. So interesting point. So they're looking at different drugs that deal with the ACE enzyme to see if it could help or hurt patients with COVID-19. So again, when that angiotensin II interacts with the ACE enzyme, it converts it. But yeah, that's the step there. And then it converts it into angiotensin II. Okay. One thing to note about this ACE enzyme is we have many, many drugs that act to block this ACE enzyme, okay? All of these drugs have a pril at the end. So lisinopril is a common one. There's many others. These are all just called ACE inhibitor drugs, and they're blood pressure drugs. So if you have anybody in your family that struggles with high blood pressure, cardiovascular disease, something like that, there's a good chance they're on one of these ACE inhibitor drugs. Very powerful effects on decreasing blood pressure because it blocks this whole system, which is all meant to increase blood pressure. Okay, so now the effects of angiotensin 2. You need to know all of these, okay? So angiotensin 2 has 4 primary effects. It promotes vasoconstriction of the blood vessels. It causes reabsorption of sodium in the proximal tubule, okay? It promotes aldosterone release, and it causes thirst and fluid intake, okay? And some of these are directly related to some of its other effects, right? We said that, so it's directly a vasoconstrictor. It causes that increase in sympathetic nervous system activation. So I'm going to just make this list match with the list that you had on the previous slide. So we see those two, which are direct effects of it. It also causes aldosterone release. So it increases aldosterone release. That one connects to this one, right? That's how we get more. Sodium reabsorption. It would also be potassium excretion, okay? And we see that here as well, okay? And then it also increases ADH release, okay? And if it increases ADH release, that's going to cause thirst and cause more water retention, okay? So then our overall effect of that is a systemic increase in blood pressure. So this is a lot here, but you do need to know the details of this renin angiotensin aldosterone system. Okay, another one that we haven't spent any time talking about, I don't believe yet, I believe this is a new one for you. It's called atrial natriuretic peptide. And where does it come from? It comes from the cells of the right atrium, that's why it's called that. And it's stimulated to be released when the right atrium is stretched out due to high blood volume or high blood pressure, okay? Its actions are to inhibit ADH, renin, and aldosterone secretion. So it stops all of those things we've been talking about. Also directly decreases sodium reabsorption. It's a vasodilator. So it does the opposite, doesn't constrict, it dilates. And then it constricts the efferent arteriole and dilates the afferent arteriole. Okay, so if we constrict the efferent, that would be opening up the part where blood is leaving. So that would make blood flow through faster. It dilates the afferent. So that would send more blood in, but then it would leave faster. So the overall effect of this is less water and sodium retention, decreased blood pressure, decreased blood volume. So this is a mechanism to get us to reduce blood pressure and volume. Okay, so what does AMP do? AMP pretty much just does the opposite of everything else we just talked about. Okay, so I'll let you guys go ahead and fill this in by using the previous slide. What effect does it have on ADH, renin, aldosterone, arterioles, overall effect? Okay, so it's just going to be the opposite there. Okay, and then the sympathetic nervous system. Sympathetic nervous system is definitely a part of this, and its effect on the afferent arterioles of the glomerulus is vasoconstriction. Okay, more sympathetic nervous system activity means we're stressed out, we want to hold on to as much water as we can, right? We don't want to let water go, so we want to send less blood into the glomerulus because we want to decrease the amount of urine, right? And that's what we see there. So the effects on blood flow of the glomerulus is decreased, which would decrease filtrate, right? Decrease urine. So I'm getting ahead of myself there, but that decrease in blood flow to the glomerulus would cause what would it do to hydrostatic pressure? It would decrease hydrostatic pressure in the glomerulus, and then that would decrease our glomerular filtration rate, okay? And then the effects, it does affect the efferent arterioles as well, just not as much, so we'll just focus on the afferent ones for now. Okay, and this just kind of briefly looks at that. If we see the glomerulus here, we see the afferent arteriole right here. See this on both sides. If we go from this one, which is constricting the afferent arteriole, to this one, which is dilating it, okay, so we're sending less blood in if we constrict it, so we're going to decrease hydrostatic pressure here. This would increase hydrostatic pressure, right? And there's a nice concept boost in your book on this on page 961, and it kind of walks you through this, but it gives the analogy of constricting our afferent arteriole is the equivalent of kind of turning the faucet down, turning the pressure down, so we don't get as much water flowing through the hose, and that would lead to less hydrostatic pressure and less fluid pushing out. whereas increasing hydrostatic pressure by dilating the afferent arteriole is equivalent to kind of turning up the faucet. Okay, so the effects on GFR, we're going to decrease GFR here, increase GFR here. Okay. All right, so this question that you have is back in your notes in the beginning. So go ahead and pause it for a second, see if you can kind of choose all that apply. Which of the following factors lead to an increase in blood pressure? Okay, so take a look at those for a sec, pause it, see if you can come up with all the correct answers. So choose all that apply. Okay, hopefully you did that. And now let's look. So definitely an increase in ADH, that causes us to hold on to more water, right? Definitely an increase in sympathetic nervous system activity because that squeezes down our blood vessels, right? Definitely an increase in angiotensin II because that causes us to hold on to more salt, which also causes us to hold on to more water as well. Also that increase in aldosterone because that's going to primarily deal with the salt portion, the sodium portion, okay? And then G, decrease in AMP, okay? Increased AMP would lead to a decrease in blood pressure, but a decrease in AMP would lead to that increase in blood pressure, okay? And those are the ones that are true. All right, so we'll kind of wrap this up here with the last little bit here, which is what we call the integrated response. And the integrated response is what looks at, we have a certain stimulus, certain change in our system, how do all those hormones and sympathetic nervous system interact with trying to get things back to normal, okay? So the first one we'll start with this is the stimulus of an increased osmolarity of extracellular fluid, okay? So this would be like getting dehydrated. We've lost water or we've added too much salt, okay? This is going to be sensed by those osmoreceptors in the hypothalamus and in the juxtaglomerular apparatus. And the two effects are we increase ADH, okay? And then the effect of that is going to be increased thirst, right? Increase water retention, okay? And then that's going to eventually lead to an increase in blood pressure, okay? But this is specifically via increased water permeability in the collecting duct, right? But then we decrease renin. Okay, so we decrease renin, so the effects of that are we actually decrease sodium reabsorption, okay? And yeah, and then again, that renin is going to, because we should say first, that's going to cause a decrease in aldosterone, okay? That decrease in renin causes that decrease in aldosterone, which then causes that decrease in sodium reabsorption, okay? Yeah, and then our final result here is this decrease in osmolarity of the blood, right? Why? Well, because we've held on to more water, increased water, but we have released sodium, okay? So we get rid of sodium, hold on to water when we have an increase in ADH, decrease in renin, and that's how we get a decrease in osmolarity of the blood. Okay, so definitely want to remember that. All right, let's look at the next one. It's just going to be the opposite. Now we have a decrease in osmolarity of the blood, or sorry, the extracellular fluid. That's sensed by those osmoreceptors, hypothalamus, JGA, that's the same. And it's just going to be the opposite, right? Now we decrease ADH, so we decrease thirst, decreased water retention in the collecting duct, right? So we decrease blood pressure. Okay, but then we increase renin in this case, right? Because there's too much water, not enough salt, right? So renin's dealing with salt, ADH is dealing with water, okay? That's the way to think about it. Even though, yes, water follows the sodium, sodium follows the water, but ADH is primarily for water, renin is primarily for salt. Okay, so increase in renin will cause an increase in aldosterone. Okay, and then we have an increase in sodium reabsorption, right? And then the final result is that increase in osmolarity. And why is it an increase in osmolarity? Because we've held on to sodium, and we've let go of water. Okay, so there's the integrated response for that one. And those are the two osmolarity driven ones, but now we have two that are volume related ones, okay? And we've got to add in two other factors now when we talk about volume. And so if we have an increase in volume of the blood, okay, so we just got too much blood volume now, this is going to be sensed by baroreceptors in the atria, okay? Also sensed by the large veins, carotid sinuses, aortic arch, and again, juxtaglomerular apparatus. Okay, so then the actions here, we decrease sympathetic tone. What would that do? That's going to cause vasodilation, right? We've got too much water in the pipes. Let's make the pipes a little bit bigger so there's not so much pressure on them, okay? That helps, okay? And then we got increase in atrial natriuretic peptide. What does that one do? It blocks ADH, blocks aldosterone, and then it also, I do need to check my notes for that one. Yes, I wanted to make sure it does block renin as well. Okay, and then it's also it increases our GFR. So increases our GFR, so that's causing more filtration to happen here. Okay, so then because of that decrease in ADH, we decrease our thirst, and we decrease water retention. Okay, and then because of that decrease in renin, we decrease aldosterone, and we decrease sodium reabsorption. Okay, so we end up with more water out, also more sodium out, right? And that's going to lead to our decrease in blood volume. Okay, so when it's a volume issue, sorry for that, there you go. When it's a volume issue, notice that ADH and renin go in the same direction, and we bring in atrial natriuretic peptide in the sympathetic nervous system. When it's an osmolarity issue, ADH and renin go in the opposite directions, and we don't think as much about the sympathetic tone or atrial natriuretic peptide. Okay, so then the last one, what about if we have too low of blood volume, okay, sensed by the same places? Instead, we increase sympathetic tone, so we vasoconstrict. That's going to increase our blood pressure, right? So we decrease atrial natriuretic peptide. So all we do on that one is we just do the opposite. We don't block ADH, we don't block renin, okay? We decrease GFR, okay? So decrease GFR. And then I won't write all those other ones, but we don't block ADH, don't block renin, don't block aldosterone. And then in this case, we increase ADH, so that increases thirst. It increases water tension, okay? And then we increase renin, which increases aldosterone and increases sodium reabsorption. Okay, so then we'd say final result is an increase in blood volume because we increased water and we increased sodium together. Okay, and so those are the integrated responses. Make sure you're very familiar with those and you can walk yourself through those. All right, guys, that's it for today.